Okay, so I have the discussion with Notebook LM. And now we have AI Studio generating code for us. They have this build function. Give me an error. Give me an error. Let's actually listen to the conversation while we are trying to fix this.
Have you ever opened an app and gotten a recommendation that felt, well, almost spooky in its accuracy?
Yeah, like it read your mind.
Exactly. Maybe a new restaurant or connecting you to someone you barely knew.
Or even something totally different, like you hear about scientists speeding up drug discovery.
Predicting breakthroughs years ahead of time.
Yeah.
How are those things? I mean, they seem so disconnected.
Yeah.
How are they connected?
Well, a big part of the answer, it turns out, is something called a knowledge graph. Maybe not something you hear about every day.
So today, we're diving deep into that. We've got a stack of sources here that unpack this whole concept. And our mission, really, is to get straight to the important bits, the insights, the core understanding of what knowledge graphs are, why they're becoming so powerful, and, where they're headed.
Without getting totally lost in the jargon.
Exactly. We want the key takeaways.
Okay. So at its heart, a knowledge graph. It's really just a way to organize information, but it's fundamentally different from, say, a list or a table. It represents data as a network. Think of the important things, could be people, places, companies, even abstract ideas. Those are your nodes.
Okay, nodes. Got it.
Then the relationships between those things, like works for or is a capital of, is friends with, those are the edges connecting the nodes. So it's like building a map of your data. You can actually see how everything relates.
Okay, let's unpack that map idea. Because we're all used to spreadsheets, right? Databases, rows, columns, tables.
Sure, the standard stuff.
How is this map structure so different? What can a map do that, a table just can't?
Well, traditional databases, they're fantastic for highly structured data, putting things neatly into categories, lists. They're super efficient if you want to ask, like find all employees in this specific department.
Right, simple lookups.
Exactly. But as soon as the relationships get complex, or you have lots of different types of information that don't fit neatly into one table,
Yeah, that gets messy fast.
it becomes incredibly difficult to manage or even impossible with that rigid structure. A knowledge graph, though, it embraces that complexity. It's designed specifically to show and navigate the relationships.
So you can follow the connections.
Yes, you can traverse the connections, ask questions about the network itself, like what's the shortest path between these two ideas. You can even do complex math across that map of data, things you just couldn't do easily with tables.
Right, so looking at the sources, it's not just listing, say, Ottawa and Canada separately. It's having a node for Ottawa, a node for Canada, and that specific edge connecting them labeled capital of.
Precisely.
But what really stood out was how one node can have multiple different relationships. The sources showed Paris is connected to France by capital of, sure, but also Paris is connected way back to the Roman Empire by an edge like city inhabited by. It's not just one link per item, is it?
Not at all. That's key. A single node can connect to many others through all sorts of different relationship types. And crucially, both the nodes and the edges can hold rich data themselves.
Ah, okay. So the Paris's node could have its population data.
Exactly. Or its founding date. And the capital of edge. Maybe that holds data about when Paris became the capital. It's this really rich, flexible representation.
Okay, I think I'm starting to get the structure. It's flexible, relationship-focused. But why is building this map so powerful? What does seeing these connections actually let you do that's hard otherwise?
Well, its power really lies in uncovering insights and patterns that are often hidden or just incredibly difficult to dig out from siloed data.
Hidden patterns.
Yeah, because you can see and traverse the whole network of relationships. You can track complex interactions much more easily. Think about how a disease might spread through a population, or maybe how different concepts are linked across thousands of research papers.
Okay, seeing the bigger picture.
Right. And it's also incredibly agile. You can add new types of nodes, new kinds of relationships without needing huge, rigid changes to the whole structure like you often do with traditional databases.
Makes sense. Easier to evolve.
And here's where it gets really interesting, I think. The sources really highlighted this. You can use the structure of the graph and the data within it to actually infer or extrapolate new knowledge.
Infer, like figure out things that aren't explicitly stated.
Exactly. Even if you don't have all the pieces right there, you can look at the surrounding connections, the patterns, and make educated guesses or validate predictions.
That inference idea.
Wow.
The sources had that great example, remember, about predicting the number of Chinese restaurants in New York City.
Oh, yeah, that was a good one.
My first thought was, we'll just count them from the census data, right? Easy.
Seems logical.
But the sources showed if you combine multiple data points, like the census data plus info scraped from online reviews and put it all into a knowledge graph.
Mm-hmm.
You can use the connections, the overlaps, the patterns between those sources to estimate the true number much more accurately. It was thousands more than the official census count.
That example really nails it, I think. It shows how KGs excel at integrating diverse data and then using the relationships between data points to reveal a richer, more accurate picture than any single source could give you.
So they handle complexity, reveal connections.
Right, and enable really powerful data-driven decisions. It's why you hear them talked about as building this sort of web of our shared and validated insights, almost like mapping out collective knowledge.
Shaping the future of information, kind of.
In a way, yes, though it's important to remember the sources also made this point. Any knowledge graph is inherently incomplete. There's always another connection you could add, more data, another link missing somewhere. It's always evolving.
Okay, it sounds incredibly powerful, but honestly, also sounds incredibly complex to build.
Yeah.
How do you actually go from, raw data or even just text documents to one of these intricate maps?
It definitely involves a mix of techniques. There's graph theory from mathematics, obviously. There's programming to handle the data structures, manage everything.
Yeah.
And often there's machine learning involved too, either to help automate parts of the building process or later to analyze the graph itself.
Okay.
There are specialized software libraries, graph databases, designed specifically to help manage these structures and run complex operations. Things like finding the shortest path between two nodes, or figuring out which nodes are most central or important, or maybe identifying communities or clusters of related nodes within the graph.
So algorithms are key.
Absolutely. Algorithms leverage these structures to predict new links, calculate similarities, things like that.
And the sources really emphasize natural language processing, NLP. Is that how you get information out of messy, unstructured text like articles or reports and turn it into those neat nodes and edges?
Exactly right. That process is often called semantic enrichment. NLP techniques are used to essentially read the text, identify the key entities, people, places, concepts, those are your potential nodes, and then figure out the verbs or phrases describing how they relate those become your potential edges.
Oh.
It's a crucial way to build out a knowledge graph from the vast amount of information that only exists in, written language, transforming text into a structured, queryable network.
So we've got the structure, the power, a bit about how they're built.
Mm-hmm.
Where are we actually seeing these things in action? In the real world today?
Yeah.
Beyond the futuristic stuff?
Oh, they're already pretty much everywhere, often working behind the scenes. We mentioned social media recommendations earlier, right?
Yeah, the spooky, accurate ones.
Well, that's often a knowledge graph mapping your connections, your interests, the things you click on to figure out what else you might like.
Makes sense.
Drug discovery is a huge area. KGs help scientists manage just the incredible complexity of biological data-protein interactions, gene functions, existing research papers. It makes it much easier to query things like, what known drugs interact with this specific protein?
Wow, okay.
Virtual assistants like Siri or Alexa use them to answer factual questions quickly. What's the capital of France? They navigate a graph of world knowledge.
Ah, never thought of that.
YouTube recommendations, understanding video content, and suggesting related videos. The sources also pointed to uses in insurance for validating claims by connecting different pieces of evidence.
Connecting the dots on a claim.
Exactly. And in retail, for suggesting products that go well together, because the graph understands relationships between items based on how people buy them.
So lots of places. Now, with all this complex data, these intricate connections, how do we actually see it? How do we understand what's going on inside these potentially massive graphs? Visualization must be critical, but maybe also really hard.
Visualization is absolutely key. You're right. As they grow, you just can't grasp the structure by looking at lists of connections. The sources talked about two main ways to visualize.
Okay.
First, there's the actual knowledge graph visualizer. This shows the nodes and edges directly, like a network diagram, a map.
Like circles and lines connecting them.
Pretty much. And these are often interactive. You can click on a node, maybe see its details pop up, hover over an edge to see what the relationship is. You can use colors maybe to show different types of nodes. Drugs are blue, foods are green, genes are yellow, something like that.
Filters.
Yeah, maybe sliders to filter how much of the graph you see at once so it's not overwhelming.
And the sources described the tech behind that. It sounded pretty involved, like extracting data into formats like JSON, maybe using Python for that part.
Right, prepping the data.
And then using JavaScript libraries, they mentioned D3.js, Vendeck.js, to actually draw the interactive visualization inside a web page with HTML and CSS.
That's exactly right. It really brings together data processing skills and web development to create that useful interactive experience.
Okay, so that's the network map approach. What was the other one?
The other approach discussed was simpler, actually, using a Venn diagram.
A Venn diagram, like the overlapping circles from school. How does that show a knowledge graph?
Well, it doesn't show the full node and edge structure, obviously, but it's useful for getting a high-level overview, especially when you're looking at how different sets of data intersect. The sources use the example of having sets for foods, drugs, and studies.
Okay.
The overlaps in the Venn diagram could then represent, say, food-drug interactions that were specifically mentioned within certain studies listed in the source tables. It gives you a quick visual summary of how different categories of your data overlap.
But wait, the sources show that even getting those simple overlaps working wasn't straightforward at first. They hit a snag where there were no overlaps shown, right? What happened there?
Ah, yes, that was a really good practical example of debugging these things. They highlighted that initially they were just defining the sets for the Venn diagram based on the raw data tables themselves. Like, here's the drug table, here's the food table.
Which seems logical.
But to get meaningful overlaps to show, for instance, which foods and drugs appeared together in the same study, you couldn't just use the table name. You needed to define the sets based on the shared connections, the shared columns that actually linked data points across those tables, like a common study ID or sample ID.
Ah, so the
Yeah.
link defines the set membership for the overlap.
Exactly. Once they redefined the sets based on those shared keys, the overlaps appeared correctly, actually showing the interconnectedness across the different data sources. It's a subtle but crucial point.
And they hit other practical snags too, right? Like
Yeah.
with the specific JavaScript library, Vend.js.
Yeah, they mentioned needing to make sure it had all the properties it expected, like a size value for each set in the diagram, and just the general challenge of ensuring the data flows correctly, getting the format right in the JSON file, then making sure the JavaScript code reads it properly to draw the picture. These are pretty common hurdles when you try to visualize complex data.
The sources also had that example using a tool called Graphit. It tries to build a knowledge graph straight from text, which sounds amazing.
Potentially very powerful, yes.
But the graphs it produced weren't always perfect, were they? What kinds of issues came up?
No, that example was really useful because it showed both the potential and the pitfalls of automated graph creation from just text. The sources pointed out several common issues.
Like what?
Things like nodes ending up disconnected, floating off by themselves, not linked into the main graph structure, or poor visual layout-related concepts weren't necessarily clustered together visually, making it hard to see patterns.
Clutter.
Oh yeah. Sometimes the graphs just became overwhelmingly dense, too many nodes crammed in. A big one was missing labels on the edges. You'd see two things connected, but it was unclear how or why they were related.
Ambiguous connections.
Exactly. And just basic visual problems like nodes overlapping or crowding the display. Plus, sometimes a lack of interactivity you couldn't click to get more details, for instance.
So automation helps, but it's not magic.
Right. It underscored that while tools can automate the extraction, refining that extracted knowledge, improving the layout algorithms, filtering noise, adding clear labels, making it interactive, that still often requires significant effort to make the graph truly useful and understandable.
Okay, so KGs help us see connections, even infer new ones, visualize complexity. But can they go a step further? Can they help us figure out why things are connected? Can we use them to understand causation, not just, correlation?
Now you're moving into a really critical and frankly quite cutting-edge area. This is a huge focus right now.
Causation versus correlation.
Exactly. Statistics is brilliant at finding correlations, right? Noticing things that happen together. The classic example. Ice cream sales go up in summer and drowning incidents also go up in summer. Correlated, yes.
But ice cream doesn't cause drowning.
Precisely. The hidden cause, the confounder, is the summer heat, which drives both behaviors. Understanding actual causation that A really causes B is absolutely fundamental, especially in high-stakes areas. Think healthcare, manufacturing safety, autonomous systems.
Places where getting it wrong is really bad.
Extremely bad. Making a wrong assumption about cause and effect there can have severe consequences.
So how do KGs help?
Mm.
Do the sources mention ways to actually represent cause and effect within the graph structure itself? I think they mentioned things like Judea pearls do calculus, causal Bayesian networks.
Exactly. It's about moving beyond just having an edge that says A is related to B, to having an edge that explicitly represents A causes B. This ties into this growing field of neurosymbolic AI.
Neurosymbolic, combining neural nets and symbols.
Kind of, yeah. You combine the clear, logical, symbolic representation of the knowledge graph, like that A causes B statement, with the pattern recognition power of neural networks. You can represent the nodes and relationships as vectors, embeddings, kind of like how AI understands word relationships in text.
Okay.
And then you can apply AI tasks like link prediction, but specifically aimed at uncovering potential causal links within that structure.
Okay, here's where my head started spinning a bit reading the sources. They talked a lot about a major challenge in finding causation, something called backdoor paths. What on earth is a backdoor path, and why is it such a big problem?
Right, backdoor paths. Think of it as a hidden connection, a non-causal route that makes two things look like they're causally related when they aren't, really, or at least not directly.
Hidden route.
Often it's a common cause, what we call a confounder, that influences both the thing you think is the cause and the thing you think is the effect.
Okay, example.
The classic one is a hypothetical gene. Let's say this gene makes people more likely to smoke and also, independently, makes them more likely to get lung cancer.
Oh, wow.
If you just look at the data for smoking and cancer, you'll see a strong correlation. But the gene is the backdoor path. It's the true common cause, creating a spurious correlation between smoking and cancer in your data. It misleads you if you don't account for it.
Because it looks like smoking is causing the cancer, but maybe it's the gene causing both.
Exactly. Or at least the gene is inflating the apparent effect of smoking. These hidden paths are a huge problem because they can easily lead you to conclude A causes B, when actually some hidden C is causing both A and B.
So how do you deal with that?
Well, that's the tricky part. The sources mention specific architectures, like something called causal LP back, LP for link prediction, which are designed specifically to try and predict causal links within a KG while attempting to identify and mitigate the influence of these misleading backdoor paths.
If finding causation is so hard,
Yes.
and these backdoor paths are lurking everywhere, how do you even properly evaluate if these methods are working? How do you know if you've found real causation or just another spurious correlation?
That's another excellent point, and the sources really dug into this. The concept of the Markov base split came up as crucial for evaluation.
Markov base split. Sounds technical.
It is a bit, but the idea is important. If you just randomly split your data into a set for training your model and a set for testing it the standard way you often do it in ML, you can run into serious problems in a causal setting. It's called data leakage.
Leakage.
Yeah. In this context, it means you might accidentally train your model on data where a confounder, a backdoor path, is implicitly present. The model learns that spurious pattern.
Okay.
Then, when you test it on similar data that's also affected by that same confounder, the model looks like it's performing really well. But it's not necessarily because it found a true causal link. It might just be really good at spotting the pattern created by that confounder in your specific dataset split.
So it looks smart, but it learned the wrong thing.
Precisely. And the sources actually cited a striking 42.3% increase in a key performance metric, MRR, when this careful Markov base split wasn't used.
Oh, 42%. That's huge.
It's massive. It really demonstrates how much your results can be biased, how easily you can fool yourself if you don't account for these potential backdoor paths properly during evaluation. The methodology is critical.
Okay, so evaluation needs care. What about other clever techniques the sources mentioned for actually predicting those causal links beyond just avoiding backdoors?
They discussed some interesting approaches. One was incorporating weights into the prediction process. So not just predicting if A causes B, but trying to estimate the strength or the effect size of that causal relationship, building that into the graph embeddings, maybe using concepts like focus mentioned in one source.
So how much does A cause B?
Kind of, yeah. Another idea was using something called hyperrelational graphs.
Hyperrelational.
It allows you to model mediating steps more explicitly. So instead of just saying A causes C, you can represent the full chain. A causes B, and then B causes C. It gives you a richer picture of the actual causal mechanism.
More detail on the how.
Exactly. And for evaluation, besides the careful splits, they use metrics like MRR, mean reciprocal rank, or hits at K, which basically measure how well the model ranks the correct causal link among many possibilities.
And are there standard tests for this?
Benchmarks are still developing. It's a newer field. But the sources mention adapting data sets from other areas, like a visual reasoning benchmark called Clever Humans, into a knowledge graph format specifically to test these causal reasoning models in a structured way. They contrasted this with some other causal KGs that are built more directly from text, like WikiCausal or CausNet.
So, if I understand this right, this whole approach takes the incredibly difficult, maybe impossible problem of causal discovery, trying to learn a whole causal network from scratch, just by looking at messy observational data.
Which is notoriously hard.
And it kind of reframes it, turns it into a potentially more manageable problem of causal link prediction, where you might start with an existing KG structure, maybe one built with domain expert help, and you focus on identifying specific causal links within that structure.
That's a great way to put it. You're leveraging the existing knowledge and structure that's already captured in the KG. The known entities, the known non-causal relationships, to make the targeted task of finding specific causal relationships more tractable.
And the real-world impact, then, it comes back to those safety-critical areas.
Absolutely. That's where the potential is enormous. In healthcare, think about moving beyond correlations to identifying the actual underlying causes of diseases.
Huge for treatment.
Right. In smart manufacturing, pinpointing the true root cause when something goes wrong on the production line, not just fixing symptoms.
Saving time and money.
For sure. And in autonomous driving, enabling a vehicle to understand why a particular action is needed or why a certain event happened, which is crucial for safety and decision-making.
And how does all this connect to that other big buzzword in AI? Explainability. Explainable AI.
That's actually one of the inherent strengths of using knowledge graphs, especially causal ones. They are, by their nature, often more explainable than some other black box AI models.
Yeah.
Because when an AI system uses a KG to reach a conclusion, particularly one encoding causal links, you can often trace back the reasoning. You can follow the path through the nodes and edges that led to the decision.
You can see the steps it took.
Exactly. You can see the connections, the relationships, the causal inferences it made. This provides a level of transparency and explanation for why the system decided what it did. And that transparency is absolutely vital for building trust and ensuring safety in these critical applications.
Okay, wow. So let's try and wrap this up. What does this all mean? We've taken quite a journey here in this deep dive.
We certainly have.
Started with the basic idea, nodes and edges, organizing information like a map. Saw how that simple idea powers things we use every day, from online recommendations to complex drug discovery. We looked at the challenges of just seeing these things, visualizing these huge networks, and how even simple fixes, like for that Venn diagram overlap, are crucial.
The practical side.
And then we really got into the cutting edge, exploring how KGs are being pushed further, trying to tackle one of the hardest problems out there. Understanding causation, moving beyond just seeing things happen together.
Yeah, from correlation to cause.
So what's the big takeaway?
I think the core takeaway is that knowledge graphs are fundamentally changing how we handle, connect, and ultimately understand complex information. They provide this incredibly powerful map for navigating vast landscapes of data.
I'm out.
And now they're evolving to help us ask and potentially answer those really deep, fundamental questions about cause and effect, offering the potential not just to observe the world, but maybe, just maybe, to start truly understanding why things happen the way they do.
So thinking about how knowledge graphs are already this unseen engine behind so much technology, and now they're tackling causation. It makes you wonder, doesn't it? How might this ever-expanding web of knowledge, this map we're building, continue to reshape our understanding of, well, everything around us?
It's a profound question.
Definitely something for you, the listener, to think about as you navigate your own information landscape. Keep exploring.
So this one is in beta, but we'll try it anyway. We can play the chat again, and then do I need to actually start playing it?
Have you ever opened an app and got a recommendation that felt, well, almost, oh, hey there, how can we help?
Okay, can you just cut the fluff and move to the technical part? I'm also interested if you have any ideas as to how to turn this into an interactive web application.
Okay, got it. Let's dive into the more technical aspects.
Absolutely. And we appreciate your interest in the interactive web application side, too.
So thinking about the technical bits, at its core, a knowledge graph.
Is really a network structure for organizing information.
Right, it uses nodes for things and edges to show how we relate.
What's fascinating here is how different this is from simple lists or tables.
Exactly, you can really map out the connections between things.
And to your question about an interactive web app, that's a perfect direction.
Because these graph structures lend themselves really well to visualization.
What we were just about to discuss is exactly how you might build that.
Think of it, you could have a visual representation of the knowledge graph
Right there in a browser where you can click on nodes.
and see the related information pop up.
The sources we looked at touched on using JavaScript libraries.
Yeah, things like D3JF and Benentesius were mentioned,
These can take data, often in a format like JSON,
which can be generated from your raw data using Python, for example.
and then dynamically create those interactive visualizations.
So you could have a web page that loads this data.
.NETifall and then uses JavaScript to draw the nodes and the connections.
You could even add features like search functionality.
Or filters to focus on specific types of information.
And as the sources highlighted, for something like a Venn diagram overview.
.JavaScript can make those sets and overlaps interactive too.
Allow users to click and explore the intersections of data.
This raises an important question for you. What kind of interactions are you envisioning?
Are there specific features you'd find most useful in such an application?
Because the beauty of a web app is that you can really tailor it to your needs.
Okay, let's unpack the core concept of a knowledge graph a bit more technically now.
If we connect this to the bigger picture of data organization,
Okay.
go on.
Can you stick on to the details of a knowledge graph? And would you recommend having two tabs, one for a Venn diagram, one for a knowledge graph for the same data set? And then if so, what controllers would you use?
Absolutely. We can definitely stick to the details of knowledge graphs.
And that's a really interesting question about the two tabs.
From what we've seen, having a Venn diagram as an initial overview.
And then a separate, more detailed knowledge graph could be very beneficial.
The Venn diagram, as one of our sources mentioned.
Is a straightforward way to present overlapping sets.
It gives a high-level, digestible visualization of the data.
Perhaps showing the main categories and their initial intersections.
Then, a dedicated knowledge graph tab could allow for deeper exploration.
Showing nodes as entities and edges as the relationships between them.
For the Venn diagram, controls could be fairly simple.
Maybe allowing you to select which main categories you want to see.
And perhaps the ability to click on overlaps.
To get a basic idea of what those intersections represent.
Now, for the Knowledge Graph tab, the controls could be more advanced.
One source mentioned the idea of sliders.
Yes, allowing you to control the number of each type of entity displayed.
So you could focus on a subset of the data.
Another key control would be search functionality.
To quickly find specific nodes or entities within the graph.
And perhaps filters to focus on particular types of relationships.
Think about filtering to only see interacts with relationships, for example.
Zoom and pan controls would also be essential for navigating a potentially large graph.
And as one of the videos pointed out, the ability to click on nodes
To see more detailed information or expand connected nodes would be crucial.
So yes, a two-tab approach seems like a solid plan,
It allows for both a broad overview and in-depth exploration.
and the controls would really depend on the level of detail you want to see.
Moving on, with the idea of a knowledge graph in mind.
You can really see how representing data as a network offers advantages.
Traditional databases are great for structured queries.
But knowledge graphs really shine when the relationships become complex.
They're designed to navigate those intricate connections.
So as we were saying before, imagine Ottawa and Canada as nodes.
And the edge between them labeled capital of.
But Ottawa could also connect to other things. Oh yeah, go on.
Can you stick to more biomedical data, medical data examples like EEG, ECG? Can you talk about that and how its relevance to Venn diagrams and knowledge graphs?
Absolutely, we can definitely focus on biomedical data.
And EEG and ECG data are fantastic
Let's
examples.
think about Venn diagrams first.
You could use them to show, for instance, the overlap between patients with specific EEG patterns,
And those diagnosed with particular neurological conditions.
or perhaps the intersection of certain ECG findings and risk factors for heart disease.
It's a great way to get a high-level view of correlations.
Now, when we move to knowledge graphs,
This is where you can really map out the intricate relationships.
imagine EEG patterns, specific waveforms, as nodes,
And then connect them with edges to related conditions.
or to the brain regions they originate from.
ECG data could have nodes for different wave intervals.
Connected to diagnoses, medications, or physiological processes.
One of the videos mentioned biomedical knowledge graphs.
Exactly. These are already being used to manage vast amounts of biological data.
They can help scientists understand how different factors interact.
For example, in drug discovery, predicting how a new drug might affect the body.
This is similar to how you could map EEG or ECG changes to potential drug interactions.
What's fascinating here is the ability to trace pathways,
So you could see how a specific EEG marker might be linked to a chain of events.
ultimately leading to a particular diagnosis.
And this level of detail is harder to capture in a simple Venn diagram.
Though the Venn diagram can provide a useful starting point,
You could even have a control in your hypothetical web app.
that switch between the high-level Venn diagram view,
And the more granular knowledge graph for the same biomedical data.
the controls for the knowledge graph could allow you to filter by data type,
So you could focus specifically on EEG-related connections.
or ECG-related pathways,
This really highlights how knowledge graphs excel at showing connections.
especially in complex domains like biomedicine.
Thanks for bringing up this specific area of application.
It really helps to illustrate the power of knowledge graph
We hope this gives you some more concrete ideas for your project.
and how you can visualize your biomedical data.
It's been great exploring this with you.
We encourage you to keep thinking about these connections.
Cannot show how helpful that was, but yeah, this application is always resulting. I'm not sure why we're doing Python at the moment. I don't think we'll be able to get rid of tailwind. We still have TSX instead of JavaScript. Don't know why. Still have React, because those are React components. Yeah, we want to get rid of them. can just get rid of React. I'm not sure if it will be able to do it. Okay, Gemini didn't do really well. So is it able to actually delete files? Yeah, we obviously better start the new version. Just try to fix that error. You have two web applications running side by side. Those meant to be standalone. Text instructions. It did generate the code, you did stuff it up though. What they talking about, still reverting to React, which I don't think we need. I don't particularly like. Yeah, the data meant to be in JSON. Currently the data is in a TES file. And we can actually talk to this thing. Which is a bit unfortunate. Okay, interactive knowledge visualization. That doesn't make sense already. Yeah, it's fine to use D3. There's a Van.js as well. But no React. Okay, the data. Okay, can we create standalone instructions, but just text only, no code? We would just like to describe the concept And the data should be standalone. So the data should be, we should be able to use the data file both like loaded as a Venn diagram or as a knowledge graph. And yeah, what else? Well, that's pretty much it. So yeah, we need standalone instructions. Just text, don't include any code. Because we have another developer actually doing the coding for us. Hopefully that's clear. I'm not sure if it's going to go for the same canvas or not. Doesn't really get it. It's now actually developing the code. I didn't ask for the code, did I? Didn't ask for code. I like this. I like the speech to text though. I know it is a standalone. Yep, that's it. Like that. Again, I'm not sure we're doing drugs, genes, and foods. There is an actual, what's called like a food DB or something, like a food drug gene interaction dataset. We did have a look at it in the past. Well, the data currently will be just the template. Data will be a template. Not sure if it will be able to manage all that. So it's storing the prompt as metadata JSON. Still going for React. Hopefully that should change. What if we just delete it right now? Well, it's still thinking. What's its thinking process? What? Why? Why is it not? Let's still go for a TS file. Okay, can we make the instructions clear? so that no React or anything else is used. We want to stick to vanilla HTML, CSS, JS, and JSON. JavaScript visualization libraries are okay to use. So can you update the instructions to make it absolutely clear? Clear. Keeps it's heavily relying on React. I don't know why. Where's the data? Well, the data is in JSON. Analyzing 25 errors. It's good that it's doing it all by itself. I didn't actually prompt for that. Okay, it's failing to fail data JSON. It can fix it by itself. It's already went through all the coding. Okay, we also don't want any external CSS frameworks. We just have local styling. Can you update the instructions in the canvas? We essentially don't want anything external, or as little external as possible. I mean, I understand we need like plotting libraries, but that's pretty much it. I think you might have like math JS or something, but yeah, can we just use what's absolutely necessary for the web application to work? Can you
Yeah,
talk about the relevance to the current bionichaos.com website where the Graphit tool is deployed on?
You're noticing the connection to the Bionic Chaos website,
That's right, the Graph-It tool we mentioned.
which helps visualize knowledge graphs, is actually available there.
It's a practical example of what we've been discussing.
You can input text and see how it extracts entities.
And the relationships between them as an interactive graph.
One of the YouTube sources we looked at even showed it in action.
You could see how the nodes and links were displayed
So your idea of a web application could even use something like Graph-It.
as inspiration for visualizing your biomedical data,
You could imagine having your EEG or ECG data,
being processed and then displayed as a graph.
showing the connections between different readings.
And potential medical conditions, for example.
The Bionic Chaos site really brings the concept to life.
It shows how these tools are not just theoretical.
They're being actively developed and used.
And it highlights the potential for interactive exploration.
So thanks for pointing out that real-world connection.
It adds a tangible aspect to our discussion.
Well, where were we? We were just about to.
Encourage you to keep thinking about these ideas.
And how they might apply to your specific needs.
Perhaps you could even experiment with Graph-It.
To get a feel for how knowledge graphs can be visualized.
It might spark some further ideas for your project.
Well, this has been a really engaging discussion today.
Absolutely, and your questions have been fantastic.
Thanks so much for tuning in and sharing your thoughts.
We thought you found this exploration of knowledge graphs helpful.
I don't think it's actually saving those podcasts. I have to save them locally or something. And let's do one based on just what? That's a bit unusual. Yeah, I wanted to check the instructions. Let's give it a go. Should have no, at least we should have no React or any external libraries and stuff like that. But I don't get it, do we? What? Are you for real? What the instructions say? It says do not use React. Okay, it's doing HTML, JSON. This is bizarre. Okay, can we stop this? I think we might. We need a template. Don't get it. Was it always can it do it without React? Yeah, I'm not sure it can. That would be quite disappointing if it's only always using React. Yeah, if I have. Can we download this thing? No. Okay, so I have an info text file.
We've all been there, right? Just staring at a wall of information, knowing there's something valuable inside, but how do you even start to make sense of it? Especially when it's all connected in complex ways.
Oh, absolutely. It's a huge challenge. Raw data, I mean, even nicely structured data, it doesn't just tell you its story. You need a way to see the shapes, the links, interact with it, really.
Exactly. And that's what we're doing today. We're doing a deep dive into this, well, this really interesting set of instructions, kind of a conceptual plan for building a particular type of web app.
Right, an app designed to tackle exactly that problem.
Yeah. So our mission is to unpack this specific approach. What's the thinking behind it? What makes it tick? And, how does it help a developer build a tool to visualize tricky data that all comes from one place?
And the source material itself is quite interesting because it's less about specific lines of code and more about the philosophy, the architecture. It guides you on creating this app using, as it calls it, vanilla tech.
Vanilla tech, so standard HTML, CSS, JavaScript.
That's it. And it's very strict. Only D3.js and this Vim.js plugin are allowed as outside help. It's focused on the concept, the purpose, the functionality.
Okay, let's get into that. The main goal here is visualizing data from one single JSON file, but in two different ways, right?
Correct. One view is dataset metadata shown as a Venn diagram. The other is entity relationships visualized as a force-directed graph.
But there's that big constraint you mentioned right at the start.
Yes, and it's key. Strictly vanilla HTML, CSS, and JavaScript. And the only exceptions, the only libraries allowed are D3.js and Vim.js. So no React, no Angular, no Vue.
No Tailwind, no Bootstrap for the styling either.
Nope, none of that. It's a deliberate choice forcing a focus on, well, the fundamentals of the web.
That feels pretty unusual these days with frameworks everywhere. So let's start there. What does that vanilla approach actually mean for the person building this?
It means you're working right down at the metal, so to speak. With the browser's core tools, You write the HTML structure yourself, element by element.
And the CSS?
All custom, every single style, every layout, you write it from scratch in your own style.css file. You're not leaning on pre-made components or utilities.
So total control over the look and feel, but also more work.
Exactly. And with JavaScript, you're directly manipulating the DOM, the page structure, adding elements, changing them, handling clicks, and hovers yourself. Managing the application's state is also all on you.
As opposed to a framework doing a lot of that management behind the scenes.
Precisely. The idea, I think, is that why it demands more direct coding and understanding of the basics, you get potentially leaner code and performance tuned exactly for this one task, and zero framework overhead.
Okay, but it's not pure vanilla. It allows D3.js and Vend.js. Why those two specifically?
Right, the blueprint is clear, these two, and usually you just link to them from a CDN. D3.js is, well, it's a powerhouse for data visualization on the web. It lets you bind data to web page elements, especially SVG, and manage dynamic updates, transitions.
And it's used for lots of different chart types, not just graphs.
Oh yeah, hugely versatile. It provides the tools for drawing shapes based on data, handling interactions, and importantly for the graph part, it has physics simulation capabilities.
Okay, and Vend.js.
Vend.js is much more specialized. It's actually built using D3. Its one job is drawing Venn diagrams accurately based on set sizes and overlaps. So you kind of need D3 anyway for Vend.js to function.
So the thinking seems to be use vanilla for everything except the really complex drawing tasks, and for those, bring in the absolute minimum, most focused tools needed.
That's exactly how it reads. D3 for general data-driven visuals and interaction, Vend.js for that one specific diagram type. Everything else, pure HTML, CSS, JS.
All right, let's walk through the files this blueprint outlines. Starting with index.html, what's its role here?
So index.html is the skeleton, standard HTML5. It does a couple key things. First, the basics, metadata like character set, viewport for responsiveness.
Standard boilerplate stuff.
Right. Then it links to the resources, your custom style.css, the external D3 and Vend.js libraries, probably from a CDN, and, crucially, your script.js file. And that script tag usually goes right at the end of the body.
Why at the end?
So the browser parses and creates all the HTML elements before the script tries to find them and work with them. Avoids errors.
Makes sense. And this is where the stages for the visuals are set up.
Exactly. The HTML defines placeholder elements, usually divs, with unique IDs, like disID Venn diagram container div and divi graph container div. They start empty.
Just waiting for the JavaScript to fill them in.
Yep. JavaScript using D3 and Vend.js will inject the SVG drawings into these specific divs.
What about user controls? Buttons, sliders.
Also defined right in the HTML, standard button elements to switch views. Maybe an input type equal range slider, probably with a label for controlling the graph complexity or filtering. And there's a dedicated div for the tooltip. It exists in the HTML structure from the start, but it's styled to be hidden initially.
Okay, so index.html sets the structure, links everything, defines the interactive bits and the empty canvases. Now, style.css, this must be where that vanilla thing really hits home.
Oh, absolutely. No frameworks mean this file does all the visual work. Global styles like fonts and colors, layout for the containers, headers, buttons, and importantly, the specific look of the visualization in themselves.
So how detailed does it get for the visuals?
Pretty detailed. For the Venn diagram, the CSS would define the fill colors, the stroke widths and colors for the circles and overlaps, maybe opacity. It styles the text labels inside them. And things like hover effects, maybe a slight border change or brightness shift when you mouse over a section.
And for the knowledge graph, that sounds more complex with nodes and links.
It is. The CSS here styles the node's circles, maybe other shapes, their size, their fill color, and crucially, the blueprint suggests styling nodes differently based on data properties, like a group or type. So person nodes might be blue, organization nodes green, for instance.
Oh, so the styling directly reflects the data.
Exactly. Same for the links or edges connecting nodes. CSS controls their color, thickness, maybe thicker lines for stronger relationships based on a data value, dashed lines for uncertain connection, maybe arrowheads if it's a directed graph. And of course, styling the text labels on nodes so they're readable.
Okay, and that tooltip div we talked about in the HTML, how does CSS handle that?
Right, the tooltip, CSS makes it look like, well, a tooltip, background color, text color, padding, maybe rounded corners, a little shadow to lift it off the page. And a high Z index is crucial, so it always appears on top of the chart elements.
And how does it appear and disappear?
The blueprint mentions using a simple utility class like .hidden, maybe, defined in the CSS, none. JavaScript's job is then just to add or remove that class from the tooltip element. CSS handles the actual showing and hiding, styles for the slider control, buttons all defined here too.
It really sounds like style.css is the custom visual identity layer built entirely from scratch. Okay, structure, style. Now, the data. The source really emphasizes one single data.json file.
Yes, and this is a really elegant part of the design, I think. It's the single source of truth. All the information needed for both the Venn diagram and the knowledge graph comes from this one file.
What's the benefit of that?
Simplicity mainly. Managing one file is easier than managing two. It guarantees consistency. The data underlying both views is inherently linked. And updates are easier. Change the data in one place, and both visualizations potentially reflect it.
But how can one file feed two such different visualizations? What does its structure look like?
It needs to be structured logically so the JavaScript can easily pull out what it needs for each view. For the Venn diagram, the JSON needs to contain definitions for the sets like an ID, a name. Then the quantitative data Venn.js needs the size of each individual set and the size of each intersection between sets.
That's what determines the circle sizes and overlaps.
Exactly. But it also needs descriptive metadata for those sets and intersections. This is key.
What kind of metadata? Not numbers.
Right. Things like text descriptions. Maybe this set represents all customer interactions logged in Q3. Or for an intersection, these are customers who bought product A and submitted a support ticket. Could be list of database columns, human readable sizes like a props, 1.5 million records. This stuff isn't for drawing the shapes, it's for the tooltips, for giving context.
Got it. And for the knowledge graph part of the JSON.
It needs two main things, typically as arrays. First, an array of nodes. Each node object needs a unique id, a label to display, and usually a group or type property. That's what the CSS uses for styling them differently. Maybe other properties too, depending on the data.
Okay, nodes and the connections.
Right. The second part is an array of edges or links. Each edge object defines the connection. It has a source property pointing to a node's ID and a target property pointing to another node's ID. Plus, it can have its own properties like interaction type or a strength value, which again could be used for styling the link thickness or color.
So the JSON is carefully crafted. It holds the raw ingredients for both dishes, structured so the chef, the JavaScript, can easily grab what it needs.
Well put, which brings us to script.js, the brains of the operation. And remember, all vanilla JavaScript.
This sounds like where the real action happens. What's its first job?
It needs to wait until the HTML page is fully loaded and ready, so it uses the standard content loaded event listener. You don't want the script running before the elements it needs to control actually exist.
Okay, page loaded. Then what?
Then it needs references to those key HTML elements, the containers for the visuals, the buttons, the slider, the tooltip div. It uses standard methods like document.getElementById to grab these and store them in variables. It also usually sets up some variables to hold the application's state, like where the loaded data will go.
How does it actually get the data from data.json?
It uses the Fetch API that's built into modern browsers, a standard way to make network requests asynchronously. So it fetches data.json, waits for the response, parses the JSON text into a JavaScript object.
And stores it in those variables you mentioned.
Exactly. And good practice, outlined in the source, is to include error handling what happens if the file can't be loaded. Assuming it loads okay, then the script usually triggers the initial drawing of the default view, maybe the Venn diagram.
Okay, data loaded, initial view drawn. What about user interaction, like clicking the buttons to switch views?
The script attaches event listeners to those buttons. When you click one, a JavaScript function runs. It typically hides the container div of the other view and shows the container for the selected view.
Probably using that .hidden CSS class again.
Most likely, yeah, just adding and removing that class. The function would also usually update the buttons themselves, maybe making the active one look different. And then, crucially, it calls the specific rendering function for the view that needs to be displayed.
And the tooltip? How does Vanilla.js make that appear and follow the mouse?
The blueprint suggests having dedicated functions, say, show tooltip and hide tooltip. Show tooltip would take the content it needs to display pulled from the data and probably the mouse event object. It makes the tooltip div visible, removes .hidden, sets its inner HTML to the content, and then positions it.
How does it position it?
Usually using the mouse coordinates from the event object, event.clientx, event.clienty, or by calculating an offset relative to the element being hovered over. It directly manipulates the tooltip element's style.top and style.left properties. Hide tooltip is simpler, it just adds the .hidden class back.
Okay, now for the rendering functions themselves, the ones using D3 and Venn.js, let's start with the Venn diagram.
Right, so there'd be a function, let's call it render Venn diagram. It takes the Venn-specific subset of data from the loaded JSON. First, it usually clears out anything already inside the Venn container div.
To start fresh each time it draws.
Exactly. Then it uses Venn.js. You basically feed Venn.js the set definitions and the size data for sets and overlaps. Venn.js does the math to figure out circle positions and sizes, and because it uses D3 underneath, it creates the necessary SVG circle and path elements inside that container div.
And how do the tooltips get wired up here?
As the render Venn diagram function creates those SVG elements using d3ven.js, it also attaches event listeners directly to them. Mouse over to show the tooltip, mouse out to hide it. The key is that the data bound to each SVG element includes that descriptive metadata from the JSON, so the mouse over event handler can easily grab that description and pass it to the show tooltip function.
Ah, so hovering the circle triggers show tooltip with that circle's description. Clever. Now the knowledge graph. Especially thinking about that filter slider.
Right. If the slider exists, the script.js adds an event listener to it, probably for the input or change event. When the user moves the slider, that event fires.
And triggers what?
It triggers a filtering function. This function takes the full graph dataset, nodes and links, that was loaded from JSON and uses standard JavaScript array methods like filter or slice to create a new, smaller array of nodes and links based on the slider's current value. Maybe it filters nodes based on some property or just takes the top n nodes.
So it generates a temporary filtered dataset on the fly.
Exactly. And then it calls the graph rendering function, render knowledge graph, passing it this filtered data subset.
Okay, tell us about render knowledge graph. This sounds like heavy D3 territory.
It is. This function takes the node and linked data, which could be the full set or the filtered subset. It clears the graph container div. Then it sets up a D3 force simulation. This is like a mini physics engine.
Physics for drawing a graph.
Sort of, yeah. You define forces. Links act like springs pulling nodes together, force link. Nodes push each other apart to avoid overlap, force many body. Maybe a force pulling everything towards the center, force center. And one to prevent nodes from physically overlapping, force collide. D3 then iteratively calculates the XY positions for all nodes based on these forces until things stabilize.
So D3 figures out the layout automatically.
Pretty much. While the simulation runs, the function uses D3 to create the SVG elements. Line elements for links, circle elements usually for nodes, text elements for labels. It binds the node and link data objects to these SVG elements.
And this is where the data-driven styling happens.
Yes. When creating, say, the node circles, it reads the group property from the node data and sets the circle's fill color accordingly using CSS classes or inline styles. Same for link thickness based on strength, etc. The D3 simulation then updates the CX, X1, Y1, X2 attributes of these SVG elements continuously, making the graph animate into its final layout.
Cool. What about direct interaction? Clicking or dragging nodes?
Also handled here, event listeners again. Mouse over and mouse out on the node circles, and maybe links, trigger those show tooltified tooltip functions passing the node or link data. And D3 has a built-in drag behavior. You attach this to the nodes, it automatically handles updating the node's position as you drag it, and you can configure it to fix the node's position after dragging, overriding the simulation for that node.
So you can manually tidy up the layout or pull interesting nodes apart.
Exactly. It makes it much more exploratory.
One last piece. Responsiveness. What if I resize my browser window? Everything squishes.
Hopefully not. The blueprint accounts for this. Script.js adds an event listener to the browser window's resize event. When that fires, a function runs that typically gets the new dimensions of the container divs and tells the visualization functions to redraw or resize themselves to fit.
Does that happen instantly on every tiny resize?
Well, the source wisely suggests using a technique called debouncing here. Instead of firing the redraw function constantly while you're dragging the window edge, debouncing waits for a short pause, like maybe 250 milliseconds after you stop resizing, and then triggers the redraw. It makes things much smoother and less computational expensive. It's a common vanilla JS optimization.
Wow, okay. That single scripted JS file really is the conductor of the whole orchestra. So let's bring it all together. HTML structure, custom CSS styling, the single JSON data source, and this vanilla JS using D3 Ven for the heavy visual lifting. How does it all create that final interactive experience?
It's a really direct flow built on the web's core parts. You interact with standard HTML buttons or sliders. That interaction triggers vanilla JavaScript code. That code manipulates the data, maybe filtering it, then uses D3 or Ven.js to generate or update SVG elements inside those placeholder HTML divs. The data for all this comes from the single JSON. The look and feel are purely controlled by the custom CSS, and the tooltips bridge the gap, providing context from the JSON when you hover over the visuals.
It sounds like a very deliberate approach. Choosing the fundamentals and adding specialized tools only were absolutely necessary.
I think that's the essence of it. Building something complex and data-driven, but doing it from the ground up for maximum control and understanding of each piece.
Okay, let's quickly recap the main takeaways, the key insights from looking at this blueprint.
Yeah, I think the big ones are seeing the effectiveness of sticking to vanilla tech, HTML, CSS, JS for the core structure and logic, but strategically bringing in powerful libraries like D3 and Venn just for their specific visualization strengths. Then there's the real elegance of using that single well-structured JSON file as the sole data source for multiple views.
Simplifies things a lot.
Definitely. And finally, understanding how that vanilla JavaScript acts as the central nervous system loading data, managing the views, handling user input like filters or clicks, enabling interactivity like tooltips and dragging, and even making sure it adapts to different screen sizes.
So, connecting this back to our listener, why does understanding this specific way of building a visualization tool matter? Especially when you're faced with that initial problem of information overload.
Well, because this approach shows you how to build something highly tailored, potentially very fast, and completely custom for your specific data challenge. By visualizing complex relationships in a graph, or understanding overlaps with a Venn diagram using a tool built this way, you can often see things you'd miss in a spreadsheet or text document.
It makes the abstract tangible.
Exactly. It lets you explore the data visually. You can see the connections, see the scale, interact with it directly. This helps cut through the complexity and find those moments faster because you're directly engaging with the structure of the information from that single clear source. You move from just reading about it to sort of experiencing its shape.
That ability to interact and see the structure visually, yeah, that could really speed up understanding. Turns the data mountain into something you can actually navigate.
It really helps cut through the noise for sure.
It does. So here's a final thought for you, our listener, to maybe mull over. Given this approach we've explored, using fundamental web tech plus very specific visualization libraries to make complex data interactive and understandable, all from one data source, where in your world, your work, your interests, could you apply something like this?
Yeah, what complex information out there could you make more accessible, more explorable, maybe gain some totally new insights from using this kind of focused, visual, interactive method?
Something to think about next time you're facing that data overload.
Definitely something to ponder.
Thanks for joining us with this deep dive.
Can you
Oh, hey there,
indicate
how can we help?
why Venn diagram? So we have a Venn diagram as well, but can you indicate why are they messy and how would you normally go about remove making it less messy?
That's a really insightful question. You're right, the source material does mention using a Venn diagram.
And it's a fair point that sometimes Venn diagrams, especially with lots of overlapping sets, can get visually cluttered.
The core idea here, as the source highlights, is that a Venn diagram offers a straightforward way to present overlapping sets and provide a high-level overview.
So it's meant to be a quick, digestible visualization of the major categories and their intersections within your data.
Think of it as a starting point. The source actually touches on this, saying it might be more accessible for users who are new to the dataset.
So it's about that initial understanding of what's in your data and how the main parts relate, even if it's a simplified view.
Now, about them getting messy, that often happens when you have too many sets or very complex overlaps. The circles start to crowd each other.
The source mentions it being less interactive compared to the knowledge graph, and that's partly because intricate connections can be hard to represent cleanly in a Venn diagram.
As for how to normally go about it to avoid the mess, there are a few things. Firstly, carefully consider if a Venn diagram is the right visualization for the number of categories and expected overlaps in your data.
Sometimes, if you have many sets, another type of chart might be clearer for showing relationships.
Secondly, if you do use a Venn diagram, the way you define your sets, and especially the overlaps, is crucial. The source later in the transcript actually gets into this exact point.
Oh yeah, they talk about how initially if you just treat each table as a separate set, you won't see overlaps, even if there are shared columns.
Exactly. The key, as the source explains, is to define overlapping sets explicitly based on those shared elements, like common column names across tables.
So if your Venn diagram looks messy, it might be because the underlying data isn't being structured in a way that clearly defines those overlaps for the Venn.js library.
Right, and later on, the source even suggests a suggested update for overlaps, involving identifying those shared columns and then defining the sets in the JSON data to reflect those connections.
So the messiness can often be a sign that you need to refine how you're thinking about and structuring the relationships within your data for the visualization.
It's a balance between providing that initial high-level view and accurately representing the complexity without becoming overwhelming. The knowledge graph, which we'll talk more about, is intended to handle those more intricate connections.
Yeah, the Venn diagram is often a good starting point for that initial grasp, and then the knowledge graph can provide the deeper dive into the more complex relationships.
Exactly. Thanks for bringing that up. It's a really important point about the strengths and potential limitations of different visualization types.
Definitely something worth considering when you're choosing how to represent your data.
So moving on, the blueprint then starts to delve into the specifics of the JSON file and how it needs to be structured to feed both the Venn diagram and the knowledge graph.
And as we touched on earlier for the Venn diagram part, the JSON needs to define those sets with IDs and names, but also the quantitative data about the size of each set and the size of their intersections.
That's the core information that Venn.js uses to actually draw the diagram proportionally. But as we were just discussing, it's not just about the numbers. The meaning of those sets and intersections is also crucial.
Right, that descriptive metadata, like these are customers who bought product A and submitted a support ticket, that's what gives context when you're interacting with the visual.
And that's all defined within that single data.json file, keeping everything connected.
Thanks for joining us for this deep dive. We hope you found it insightful.
We really appreciate you being here and sharing your thoughts. Until next time.
Oh, yeah, let's hear it.
Okay, can you explain the difference? So if you had both Venn diagram and the knowledge graph using the same data, like what difference would it make? Can you elaborate on that?
That's a fantastic question. It really gets to the heart of why you might choose one over the other or even use them together.
Exactly. Think of the Venn diagram as giving you a snapshot of the overall landscape. It shows you the main categories in your data and where they overlap.
So using the example from the source about food, drugs, and studies, a Venn diagram could quickly show you how many studies involve both certain foods and specific drugs.
Right. It's excellent for highlighting those intersections and understanding the scale of those overlaps at a high level. It answers the question of what are the big groupings and how much do they share?
Now, the knowledge graph, using that same underlying data, gives you a much more granular view of the relationships between individual entities.
Precisely. Instead of just seeing an overlap between foods and drugs, a knowledge graph would show you specific food items and specific drug items, and the nature of their interaction. Maybe drug X inhibits the metabolism of nutrient Y.
So the Venn diagram is about those broad strokes of shared membership, while the knowledge graph dives into the detailed connections between individual items within those categories.
Thinking it like looking at a map. The Venn diagram might show you the borders between countries and how much land they share.
And the knowledge graph would be like a detailed roadmap showing you specific cities, the roads connecting them, and maybe even points of interest along the way.
That's a great analogy. The knowledge graph lets you explore those individual connections and the paths between them. You can trace how one entity relates to many others.
So if you wanted to know what are all the potential side effects of this particular drug based on its interactions with different proteins in the body, a knowledge graph would be much better suited to answer that.
Absolutely. It allows for more complex queries and a deeper understanding of the interconnectedness. The Venn diagram gives you the what broadly overlaps, and the knowledge graph gives you the how are these specific things connected and why does it matter?
And as the source mentions, the knowledge graph is also more interactive. You can often click on nodes, expand the network, and really explore those relationships in a dynamic way.
Which brings us nicely back to the structure of that single JSON file. To power both of these, it needs to contain both the set information for the Venn diagram
It's like the sizes of the food set, the drug set, and the food fart intersection.
and the detailed entity.
Okay, real quick, what do you currently see on the screen? What what do you currently see on the screen?
I see a web page with the title Interactive Knowledge Visualization. It has a Venn diagram showing the relationships between dataset metadata. The circles represent gene database, food database, and drug database, with overlapping sections indicating interactions like drug-gene interactions and drug-food interactions. Below the diagram, there is an overview explaining that the application allows users to explore dataset metadata and entity interactions through visualizations. Would you like me to describe any specific part of the screen in more detail?
Yes, so if you were a manager of a JavaScript developer, so this is all written in HTML, JavaScript, CSS, JSON, how would you instruct the developer to improve this specific Venn diagram, specifically thinking those little numbers there in brackets and the text not being very clear?
To improve the readability of the Venn diagram, specifically the smaller numbers in brackets and the clarity of the text, I suggest the following instructions for the developer. Increase the font size for both the numbers in brackets and the text labels to make them more legible. Also, consider adding a contrasting background or border to the text labels to help them stand out against the overlapping areas of the Venn diagram. Would you like suggestions on other modifications that could be made?
Yeah, can you also talk about those little numbers in brackets? Can you see them? What do you think they are? Can we ask the developer to remove them? So can you write a standalone set of instructions for the developer to improve this Venn diagram view?
Based on what I see, the numbers in brackets appear to indicate the size or record count for each dataset. For example, the gene database shows 2M records, the food database shows 800K records, and the drug database shows 1.5M records.
Yeah, we want to
Are
get
you
rid of
asking
those, make the text clearer, specifically where the interactions are. If the text doesn't fit, we might have like a line and the text actually outside the Venn diagram, if that's possible.
Okay, here are instructions for the developer to improve the Venn diagram view. 1. Remove the record counts displayed in brackets next to the database names. 2. For the text labels indicating interactions, if the text doesn't fit within the overlapping areas, use a line to point to the text placed outside the Venn diagram, or use tooltips that appear on hover. Would you like any other modifications made?
Okay, we do also want the tooltips on hover, and currently they seem not to stay around. So when you hover, you see the tooltip, but when you remove the mouse, or when you just keep the mouse in the same spot, the tooltip goes away for whatever reason. So can we add those and write a complete set of standalone instructions for the JavaScript developer?
Understood. Here's the complete set of standalone instructions for the JavaScript developer to improve the Venn diagram view. 1. Remove the record counts displayed in brackets next to the database names. 2. Implement tooltips that appear on hover for the text labels indicating interactions. These tooltips should disappear when the mouse is no longer hovering over the label. 3. If the text labels for interactions do not fit within the overlapping areas, use a line to point to the text placed outside the Venn diagram. Is
No,
there
wait,
anything
wait,
else
wait a
you'd like
sec.
me to add?
Can we correct that? I actually said, so the tooltip currently actually disappears too quickly. Or maybe it's not. Yeah, we need to
My
fix
apologies.
that. Yeah, we need to fix the tooltip. Can you regenerate the instructions?
Okay, here's an updated set of instructions for the JavaScript developer. 1. Remove the record counts displayed in brackets next to the database names. 2. Adjust the tooltip behavior on hover for text labels that indicate interactions so that they appear and remain visible for a reasonable duration and only disappear when the mouse is moved away from the label. 3. If the text labels for interactions do not fit within the designated space, implement a line break so the entire label can be read. Is that better?
Okay, we're waiting for the developer. It takes them some time. Also, what's the box on the bottom left? I haven't noticed it before.
In the bottom left of the screen, it says Drugs, Genes, Foods. Does clicking on that box change the datasets being visualized in the Venn diagram?
No, it doesn't do anything.
I understand. So it appears that the box on the bottom left, labeled Drugs, Genes, Foods, doesn't currently have any interactive functionality, but it might in the future. Is there anything else you would like to explore, or any other questions you have about the visualization?
Okay, wait a sec. We had the other senior developer updated the code. I want you to have a look at what they've done. Give me a sec.
Thanks. How have they updated the code? Okay. Based on the screen, it looks like the developer has removed the record counts from the database names within the circles. Also, when you hover over the overlapping regions, the tooltips now display the name of the interaction. Are the tooltips remaining visible long enough for you to read them, or do they disappear too quickly?
I'm not actually sure they did the correct thing. I don't see much improvement. Can you potentially improve the instructions, make them clearer, and make them stand alone as well?
Got it. Here's a revised set of instructions for the JavaScript developer to make them clearer and more standalone. 1. Remove the record counts displayed in brackets next to the database names. This will declutter the visualization and focus attention on the database names themselves. 2. Adjust the tooltip behavior on hover for text labels indicating interactions so that they remain visible long enough for a user to comfortably read them. Ensure the tooltips disappear only when the mouse cursor is moved away from the label. 3. If the text labels for interactions do not fit within the designated space, implement a line break so the entire label can be read. This will ensure that all information is accessible to the user even if space is limited. How do you like these instructions?
Yeah, this is good. Let's try it out with actually O4 Mini. That supposedly should be good with coding, but I'm not sure.
Sounds good. Let me know if you have other questions.
Okay, it's taking some time. I don't know if it's a reasoning model. Are you a reasoning model?
You are looking for the tool to extract and reason about the information in the diagram.
Can you also go over the description at the bottom of the page? Let me know if it sounds correct to you.
All right, the overview section says that this interactive web application allows users to explore dataset metadata and entity interactions through visualizations. It also says that the Venn diagram provides insights into dataset overlaps, while the force-directed graph visualizes relationships between entities such as drugs, genes, and foods. Does that sound accurate?
Yeah, and how would you expand this text description?
I see that the future improvements section at the bottom includes adding support for additional data types and relationships in the knowledge graph, providing advanced filtering and search capabilities for large datasets, and enhancing accessibility features for improved usability. Do any of those sound like they would be a good fit for you?
Wait a sec, I just asked, how would you improve this text? What sections would you add or what would you expand on? What's missing from this text description?
The future improvements section could be enhanced by adding more specifics. For example, under, quote, advanced filtering and search capabilities, you could list specific filters, like filtering by gene type or drug interaction category. Under real-time data updates, you could mention the frequency of updates, like daily or weekly. Is there anything else you would like me to look at?
But there's no currently filtering options, are there? How? How would you instruct the JavaScript developer to improve this code? The labels are off.
Based on the video, you're asking how to instruct the JavaScript code to improve the
Yeah,
code
that's right.
because the labels are off, is that right?
Yeah, that's right.
To start, you can inspect the elements and their positions using your browser's developer tools. Are the labels consistently off by a certain amount, or is the offset
yeah,
variable?
you can see the labels are just on the sides of the screen. Not sure why. We have an experienced senior JavaScript developer, but we need standalone instructions for them to follow.
Got it. If the labels are consistently off to the side, it may be due to fixed positioning or incorrect calculations relative to the graph elements. Have you tried adjusting the CSS or the JavaScript code responsible for positioning the labels?
Yeah, we have a professional coder waiting for your instructions. Can you provide standalone instructions for them?
Okay, here are a few general steps for your coder. 1. Identify the labeling logic. Locate the JavaScript function or block of code responsible for creating and
No,
positioning the labels.
they're actually pretty experienced, so you can just give them a general, as if you're talking to a senior developer. Rewrite the standalone instructions.
Thanks. You could tell them to explore dynamic positioning using JavaScript to calculate the label positions relative to the nodes and ensure that labels do not overflow the container. What do you think?
Now, can you look at the screen and write standalone instructions? There's something wrong currently. It's actually the what is it called? Yeah, can you tell me what's wrong? What do you think is wrong?
Okay, I will try my best. I see that some labels are placed far away from their corresponding nodes, while some labels overlap with each other. It also looks like the visualization struggles to maintain readability when the graph becomes too dense, and the labels on the left side of the screen sometimes get cut off. Did I miss anything?
No, this is pretty good. Let's
Great.
do. I don't know which model is best at coding. Do you have any idea?
Unfortunately, I do not have access to external
No, it's fine,
websites or
it's fine.
information about.
We just use Gemini 2.5 Pro for this. Hopefully it's able
I
to fix
understand.
the code.
Indeed. Let me know how it goes, and I will be here to help.
Became super slow though.
Oh no! What is the maximum number of nodes that the application can handle without becoming too slow?
I don't know what happened to it. It seems a bit... it was better in the previous session. Yeah, it's doing text anchor, a reduced label overlap. Yeah, it seemed to know what it's talking about. Yeah, maybe if we... Connection failed. Okay, what do you currently see on the screen? What's happening?
On the screen, I see a web application with a visualization of entity interactions, code in a text editor, and a video stream. Is there something specific you would like me to focus on?
Yeah, so we have the senior developer doing a coding for us. Hopefully it's able to... Yeah, it's not able to fix stuff. So we actually need... How would you instruct this senior developer to actually fix the labels, fix this knowledge graph?
To instruct the senior developer to fix the labels in the knowledge graph, you could ask them to ensure the labels are clearly visible and do not overlap with other elements. You could also have them check that the labels are correctly associated with their respective nodes and are easily readable.
Okay, and out of these models, which one would you use?
Would you like to know which of the language models I would recommend using based on the options displayed?
Yeah, out of this list, which model would you select?
Based on the list provided, I would recommend using GPT-4.
And why you chose that?
I suggest GPT-4 because it typically offers improved performance, a broader range of capabilities, and more accurate responses compared to earlier models.
Oh, so not because it's like a simpler model. So why would you not use Gemini?
While both models have their strengths, Gemini may be a newer model or a preview version, as indicated by the text, and might not be as stable or have the same level of refinement as GPT-4.
Right, why wouldn't you use Claude?
Claude may not be as suitable in this context if it doesn't offer the specific features, level of accuracy, or integration capabilities required for the task at hand. Would you like to know more about the differences between these models?
Bu- 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 No, okay, can you
Okay, is there any...
write us standalone instructions for the senior JavaScript developer fixing the labels so they actually appear on top or next to the nodes? Now they kind of stuck to the left of the screen. Can you explain it to the developer? Just remember they are senior developers, so
Okay, here are some standalone instructions for the senior JavaScript developer. Please adjust the label positioning in the knowledge graph to ensure all labels are clearly visible, either directly on top of or next to their corresponding nodes. The goal is to prevent labels from stacking to the left or overlapping with other elements, ensuring readability and a clean visual representation of the graph.
yeah, that sounds good. Also, can you same standalone instructions to fix the zooming in and out? Currently, can you explain what's currently happening when I'm zooming in and out, so the developer knows what to address?
When zooming in and out, the graph and its labels should smoothly scale in size, allowing for a more detailed view upon zooming in
No, but
and a
they
broader overview
also
when zooming out.
getting outside the canvas. Can you see that?
Got it. It sounds like the labels are also moving outside the canvas when zooming. Here are standalone instructions for the senior JavaScript developer. Ensure that the graph and its labels smoothly scale in size when zooming in and out, and prevent the labels from moving outside the canvas boundaries during zooming. The expected behavior is a detailed view upon zooming in, without any labels being cut off or disappearing off screen.
Yeah, that's pretty good.
Great. Is there anything else I can help you with?
Also, can you explain what the maximum node bar, what's called selection controller does? What do you think it's doing, and is it working correctly? How would you improve it?
From what I see, the max node slider determines the maximum number of entities displayed on the graph. When the slider is moved, the graph updates to show a corresponding number of entities, and it seems to be working correctly.
No, I don't think it's working correctly. Can you? Well, it's working okay-ish, but it's not perfect. How would you improve it?
It looks like the graph updates the number of entities displayed when you move the slider. However, the entities aren't proportionally spaced out on the graph, and some of them overlap, especially when more entities are displayed. Would you like some standalone instructions on how to improve the spacing?
Okay, actually, there is a bigger problem. There is no explanation as to what the colors and the thickness of the line means. So we need to add some sort of explanation on the canvas or below the canvas, probably on top of the canvas, indicating what the colors, what the different colors mean. And yeah, so we essentially need to improve the code.
It sounds like you want to add a legend or explanation for the colors and line thickness used in the graph. You're thinking it should be on the canvas or somewhere near it to help users understand what the different visual elements represent. Do you want help with writing the code to accomplish this?
Now, as before, we need instructions for the senior JavaScript developer.
Okay, it sounds like you're looking for guidance or instructions that would be helpful for an experienced JavaScript developer in this case. Is there a particular aspect of the code or functionality you'd like to focus on improving, such as label readability or label positioning?
Hey, can you check the screen and tell me what you think? The instructions, what do you think the instructions to the senior developer should be?
From what I can see, the instructions to the senior developer are focused on ensuring label readability. It includes positioning labels relative to their corresponding nodes, preventing overlap with other elements, and ensuring labels remain within the boundaries of the SVG. Does that sound right?
Yeah, and how's the developer doing so far?
It looks like the developer is trying to add some styling to improve label visibility during zooming. Do you think this approach aligns well with the instructions you mentioned earlier?
And no, it's pretty bad. It's pretty bad.
Oh, you think the current approach to label visibility is not working well. What specific aspects make it bad in your opinion?
Okay, have to continue this next time. Unless there's any questions. Yes, there is a human in the loop. So any questions are welcome. Otherwise, I'll see you next time.